So we're classifying electrons in our polar covalent bond or non-polar covalent bond. And we remember that covalent bonds, you have two atoms. Between those two atoms, they're sharing the electrons, and they're sharing them evenly or very close to evenly in a non-polar bond. And in a polar bond, the more electronegative atom, like fluorine in this example, will have a partial minus. This will have a partial plus. And this bond is like a little magnet. It's not a full plus and a full minus, but think of it as like a minus 0.8. Okay, so hydrogen to hydrogen. This is a tug of war with itself. So nobody wins. Oops. Don't know what happened there. Non-polar. OH. So look at your periodic table. Here's your oxygen. Hydrogen's all the way over there. First thing I do when I'm doing electronegativity is pop hydrogen in where it should be for its electronegativity trends. Oxygen's farther to the right, more electronegative. So the thing that's more electronegative will always have the partial minus in it, partial plus, and this is a polar bond. It's a very polar bond. Partial plus, more electronegative atom gets the partial minus, and this is a polar bond. Let's do HF. So hydrogen and fluorine. Hopefully you remember fluorine is the most electronegative atom in the tug of war. It's definitely pulling the electrons towards it. That gives this fluorine a partial minus and hydrogen a partial plus, and it is a polar bond. It's definitely a polar covalent bond. Partial plus, more electronegative atom gets the partial minus, and this is a polar bond. CC, tug of war with yourself. Nobody wins, non-polar. And H. N is more electronegative than hydrogen. Partial plus, partial minus. This is a polar covalent bond. OO, tug of war with yourself, non-polar. So up until now, it was pretty easy because if the atoms were different, it was a polar bond. And if they're the same, it was non-polar. But CH, these are very close to each other. It's a memorize task, right? You learned that in the videos. And it's a non-polar bond. And you'll see them in lipids. They're very important in your body. And they're just not different enough for it to be polar. Okay, so the next question, we've given you an electronegativity scale. We've deleted the D block just so it fit nicely in this little spot. So don't be confused. If you looked on the periodic table, lithium blue, what we've done is we've cut off, we have this, and we said we don't have room for that. And then we did this. Okay, so you have your metals and you have your non-metals. And it says create an ionic bond. So what do you need for to have an ionic bond? Ions, right? And the easiest way to do it, pick a metal, pick a non-metal. Maybe you picked a group 2 metal. Beryllium would have a +2, so you need 2 fluorides. Maybe you picked lithium chlorine. All of those are ionic bonds. Okay, now we want the most polar covalent bond possible. So the largest difference in electronegativity while still maintaining a polar covalent bond. It still needs to be covalent. So for this example, I can't use a metal because otherwise it would be an ionic bond. The least electronegative one shown is silica, Si. And the most electronegative is fluorine. So that is our most polar covalent bond possible. It's very partial minus partial plus. Picture a very strong magnet between these two. Not between these two. These basically form a little magnet. Okay, so create the least polar covalent bond possible. Least polar covalent bond. This is a weird question. Okay, so for it to be polar covalent, it has to be 0.5 or more. I mean, sorry, more than 0.4. It has to be more than 0.4. So you look for this, and I'm going to pick N and O because it's officially a polar covalent bond, but barely makes the cut. I did not mean to ask this question, actually. So this is not the most important thing. Really, I just wanted to ask you for a nonpolar bond that was 100% pure nonpolar. For example, like HH is nonpolar, nonpolar, nonpolar versus CH, even though it's classified as nonpolar, there's a little slight difference in electronegativity. So don't freak out about number 4. This is not a question I would ask on the exam because I really don't want you worrying about those tiny little details. Okay. So in your body, the two most important nonpolar covalent bonds, it's really, really important. Our CC and CH bonds, they're nonpolar. It's going to dictate how things are soluble, where they're soluble, how they interact. If you're taking 1050, you're going to appreciate knowing this. And 2 important polar covalent bonds you'll find in your body. NH, OH, maybe you said CN, CO, maybe you said PO. All of those are great polar bonds that are very important in your body. DNA, proteins have all of these bonds in there. Well, not the PO bond. You'll find that in your DNA and in other locations. Okay, so let's switch gears and talk about solutions and electrolytes. Solute. That's the small thing. Solute, so cute. So the quantity, smaller quantity. In a solution, solvent's the larger quantity. Solution, you combine 2 things and it has to be a homogeneous solution, meaning all the same throughout. Solubility, does it dissolve or not? Okay, so identify the solute and the solvent. Solute, so cute, the smallest amount. Solute, 5 grams versus 50. 5 grams is the smaller quantity. So that's my solute. Four versus 1,000. Definitely 4 is the smaller quantity. That's my solute. So cute. 20 versus 2. 2 is the smaller quantity. So that is my solute. And my 2 versus 2 versus 20. The 2 is the smaller number. So that's my solute. Solute, solute, solute. You'd put your solutes, and when you combine it with 50 grams, that's the solvent. Solvent, the larger quantity, larger quantity, larger quantity. And all of these, it's assumed that it makes a homogeneous solution. When we combine these, it forms a homogeneous solution. Okay, so which of the following could be classified as a solution? A is an O. Why not? Because it's a heterogeneous solution. You can see that the oil and the water are not forming one uniform throughout solution. NaCl and water have been combined. Yes, this is a solution. Some sort of sugar and water have been combined. Yes, it's a solution. This one's not. Why not? It looked like it at first, right? You're like, oh, yay, it's homogeneous throughout, but it's just water. There's no other thing combined with it, so it's not. So B and C are the answer. If you have an aqueous solution of sodium chloride, so we have this solution. I'm going to picture it for each one. I'm going to start off with that same solution. I'm going to start off with a solution. If you've read the questions, you'd know that. It's okay if you didn't yet, right? You're checking your answers. So we add more NaCl. I put more salt in here. My concentration increases. If I add more water, and I had salt in there, it's going to be less salty, right? The concentration, so the concentration decreases. If I have an aqueous, I boil off some water. So I took my solution and I boiled off a bunch of water. It's going to be saltier. Concentration increases. So what's going to decrease the concentration? If I add solute, that's the opposite. So if I add solute's the small thing. I'm picturing I have my solution and then I add a bunch of salt in there. That's going to make it saltier, increasing the concentration. Adding solvent. So if I have a salty solution, I add a bunch of water, that's going to make it, that's going to decrease the concentration. If I remove solvent, that's the opposite. So of course, D is not the answer either. So B. Okay, what is an electrolyte versus a non-electrolyte? They're both water soluble. They dissolve in water. And one forms ions. Forms ions or not? If it does form ions, it's an electrolyte. If it doesn't, it's a non-electrolyte. Okay, so NaNO3, the ionic bonds, Na plus, NO3 minus, you recognize that as your polyatomic ion. They dissolve in solution. When they dissolve in solution, you put them in water. So plus water, I get Na plus. The ions that you have in the ionic compound, the ions are going to stay the same, but now because it's in solution, we say AQ. NO3 minus, it's no longer ionically bonded to sodium. They had an ionic bond, we add water to it, and now it's just floating in solution, aqueous. Magnesium chloride, it's ionic, so we know it can break apart. We put it in water, and when we do, you look up on the periodic table, magnesium would have a +2, fluoride has a -1, and we have 2 of them. BaNO3, it's an ionic compound. We know when we add water to it, we'll get barium, AQ, and NO3 minus AQ, and I have 2 of them, which makes sense, right? It has a +2, nitrate has a -1, so I should have 2. Bromine, so you're chugging along, feeling good, and then we get to a covalent compound. Do covalent compounds break apart? They do not. So Br has a covalent bond, and it's just chilling like this. Does not break apart to form ions. So, but let's assume these are soluble in water. So soluble in water, but it's covalent. So we call it an electrolyte, non-electrolyte. Dissolves in water. It's important, but it does not break into ions. CH4 is another covalent compound, right? It's methane. Cows are tooting it. Methane and covalent bonds. So it's a non-electrolyte, assuming it dissolves in water. Okay, so let's do similarity. You have 12.9 grams of NaCl. We want to know moles. Do we have a relationship between grams and moles? Grams and moles, grams and moles. Yes, we do. Molar mass, that could convert grams to moles. So we have to calculate the molar mass of NaCl. I need my periodic table. So here's Cl, 35.453, and Na. I'm going to add those two together to get the molar mass of NaCl. 22.999 plus 35.44. 58.452 grams per mole. So I'm going to use that to get how many moles of NaCl I have. I need to get rid of grams on the top, so I'm going to put grams of NaCl on the bottom, moles of NaCl on top, and I have 58.452 grams in 1 mole. And then all I need to do is calculate it. So 12.9 divided by 58.452. And I need three significant figures, 0.22069, 0.221 moles. Moles are left over. My grams of NaCl canceled, moles. I should always, before I even bother calculating, I should make sure that this and this cancel. So if I made a mistake, I can fix it there before I 3 steps in. Okay, let's do the next one. 2.92 grams NaCl. I want to get rid of grams of NaCl. I want to know moles, so I need moles on top. What's the relationship between grams and moles? The molar mass, 58.452 grams in a mole. And I need 3 significant figures. So these are leading zeros. They don't count. 1, 2, 3. I need to have 3. This rounds up to that. Okay, and that's how you do it.